Right now, sunlight is pushing on you. Every ray that lands on your skin gives your body a tiny shove. You cannot feel it. It is real, and it never stops. Here comes the strange part. Light has no weight. It carries no mass at all. A beam of sunshine weighs nothing. So how can nothing push something? How can a thing with zero mass move a comet, spin an asteroid, or hold up an entire star? Today we chase that answer across space. We ride a spacecraft driven only by light. We watch giant stars fight their own glow. We meet a beam that could one day carry us to another sun. If mysteries like this pull you in, hit like and subscribe so you never miss one. The push is real. The reason is stranger. Let's begin. Hold out your hand. Look at your palm in the light. Something is landing on it right now and something is pushing back. Sunlight is touching your skin. Each beam carries a tiny amount of push, and when it hits you, it presses down. The push is soft. Far too soft to feel. If you stood in bright noon sun for your whole life, the total shove would still be gentler than the weight of a single grain of sand resting on your finger. You have felt real pushes before. A friend shoves your shoulder. Wind leans against your jacket. A wave knocks you sideways at the beach. Every push like that comes from something solid or heavy slamming into you. A hand has mass. Wind is moving air, and air has mass. Water has mass. When they hit you, they hand over some of their motion, and you feel the bump. Light is different. Light weighs nothing. A flashlight beam has no mass. A sunbeam pouring through your window has no mass. You could fill a room with light, seal it shut, and the room would weigh exactly the same as before. So light should not be able to push at all. A thing with no weight should slide right through you and leave you alone. Yet, it pushes. Scientists have measured it. They built machines that catch the shove of a beam and prove it is there. The force is real, steady, and always aimed away from the source. Sunlight is nudging your body outward, away from the sun, every second of every day. Think about how strange that is. Something with no mass is moving matter. It moves your skin by a hair. Out in space, that same push moves whole spacecraft. It steers rocks the size of mountains. It even holds up the crushing weight of a star. The push is weak on Earth, and enormous out where nothing gets in its way. Here is the puzzle that took the smartest minds 200 years to crack. To push something, you normally need momentum. Momentum is the punch a moving object carries. A truck rolling down a hill has huge momentum. A rolling marble has a sliver of it. The rule scientists trusted for centuries said, momentum comes from mass times speed. No mass means no momentum. No momentum means no push. Light breaks that rule. It has no mass, yet it carries momentum anyway. It can strike an object and deliver a kick, like a ghost that weighs nothing but can still knock over a cup. This one strange fact ripples out into almost everything in space. It decides why comet tails always point away from the sun. It powers ships that sail on nothing but sunshine. It lets scientists grab a living cell with a beam and lift it without touching it. It keeps giant stars from crushing themselves into nothing, and it might, one day, carry humans to a star we can only see as a dot in the night sky. To understand any of that, we have to answer the first question. How does something with zero weight carry a punch at all? For a long time, nobody knew. The best physicists of their age argued about it, and most of them guessed wrong. The answer starts with a man scribbling equations by candlelight, chasing a hunch that light and electricity were secretly the same thing. Before we meet that man, we need to understand exactly why this problem drove scientists mad. Picture a game of pool. You slide the white ball across the felt and it slams into a red ball. The red ball shoots off. The white ball slows or stops. What passed between them was momentum, the punch of a moving thing. The white ball had mass and speed, so it had momentum, and it handed some over on impact. Now shrink that idea down. Everything that pushes in your daily life works this way. A hammer drives a nail because the hammerhead has mass and swings fast. A soccer ball flies because your foot, with real mass behind it, transfers a punch. Even the air pushing a sailboat is trillions of tiny molecules, each one a microscopic ball with mass drumming against the sail. For hundreds of years, this looked like an unbreakable law. Momentum equals mass times speed. Feed in zero mass and the math spits out zero. A thing that weighs nothing should carry no punch. Ever. It could travel 1,000,000 miles an hour and still land like a shadow. Shadows do not knock things over. So when a few scientists whispered that light might push on matter, most people laughed. Light weighs nothing. Everyone agreed on that. Therefore light must carry no momentum. Therefore light cannot push. The logic felt airtight, the way a locked box feels airtight until someone finds the hidden key. There were hints something was wrong. People had noticed for centuries that comet tails always stream away from the sun. A comet flies toward the sun with its tail trailing behind, then swings around and heads back out, and the tail flips to lead the way, still pointing away from the sun. Something was blowing that tail like an invisible wind pouring off the sun in every direction. Nobody could name the wind. The old law had a crack in it, and the crack was this. Momentum equals mass times speed works for slow, everyday objects. It is a shortcut correct for baseballs and trucks and marbles. But it is only part of a bigger, deeper rule, and that deeper rule does not need mass at all. It needs something else, something light has in huge supply. That something is energy. Light is pure energy on the move. A sunbeam is a river of energy racing at the fastest speed anything can go, 300,000 miles every second. At that speed, energy itself starts to behave like it has a punch, even with no mass riding along. This was the hidden key. Momentum can come from energy alone if that energy moves fast enough, and nothing moves faster than light. Light is energy travelling at the absolute limit of the universe, so light, weighing nothing, carries a real and measurable punch. That sentence is easy to say now. In the middle of the 1800s, nobody had proven it. It was a wild guess sitting in the mind of one Scottish physicist, buried inside a set of equations so beautiful that other scientists called them a work of art. He was not trying to prove light could push. He was trying to explain electricity and magnets, and when his math was finished, out fell a prediction so bold that he could barely believe his own numbers. His name was James Clerk Maxwell, and he was chasing lightning. In the middle of the 1800s, electricity and magnets seemed like two separate mysteries. A magnet stuck to iron. A wire carried a spark. Nobody was sure how the two connected. Maxwell sat down to write the rules that tied them together, filling page after page with equations. What he found stunned him. His math said that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. One feeds the other. If you jiggle an electric charge, it makes a magnetic ripple, which makes an electric ripple, which makes another magnetic ripple, on, leapfrogging forward through empty space. That leapfrogging ripple was a wave, and when Maxwell calculated how fast his wave should travel, the number that came out made his hand freeze. It was the speed of light, exactly the speed of light, which other scientists had already measured by different means. That could not be a coincidence. Maxwell realized he had stumbled onto the secret identity of light itself. Light was not some special glowing substance. Light was an electric and magnetic wave rippling through space, the same as the invisible waves his equations described. Radio, heat, the glow of the sun, all of it was the same thing at different sizes. Then his equations did something even bolder. They said this wave should carry momentum, not by having mass since the wave has none, but by carrying energy at top speed. Maxwell's math showed that when the wave slams into a surface, it should press on it. Light should push. He even calculated how hard. The answer was almost nothing. Sunlight falling on a surface pushes with a force so small that to feel it, you would need to catch the sunshine landing on an area the size of a football stadium and squeeze all that push onto a single fingertip. Even then it would barely register. On the whole face of a large house, the push of sunlight adds up to about the weight of a small coin resting in your palm. So light did push, but only by a whisper. That was the good news, and the bad news at once. Good, because it meant Maxwell was right and the old law had a loophole. Bad, because a push that faint would be a nightmare to measure. Any breath of air, any speck of heat, any tremble in the room would swamp it completely. Maxwell published his prediction and moved on. He died young, at 48, never seeing anyone catch the push in a lab. He left behind a claim written in ink but not yet proven with a machine. Light presses on matter. He was sure of it. The world was not. For years his prediction sat like a dare. Somewhere out there a beam of light was pushing on everything it touched. and no experiment on Earth was delicate enough to catch it in the act. The push was hiding inside a storm of stronger forces, heat and air and vibration, all 1,000,000 times bigger. To prove Maxwell right, someone would need to build the most sensitive machine of its age, remove nearly every trace of air, and catch a force lighter than a shadow's weight. One man in Russia decided to try. Before that man built his machine, nature had already left a giant clue hanging in the night sky: comets. For as long as humans have looked up, comets have terrified and amazed us. A comet is a dirty ball of ice and rock, often only a few miles across, smaller than a city. Most of the time it drifts in the deep cold far from the sun, dark and silent. Then its long orbit swings it inward, and something wakes up. As the comet nears the sun, the ice starts to boil away. Gas and dust stream off the little ball and form a glowing tail. That tail can stretch for millions of miles, longer than the distance from Earth to the sun, all pouring off a lump of ice the size of a town. A comet is mostly a small dark rock trailing a river of light across half the sky. Here is the clue that puzzled skywatchers for centuries. The tail never trails behind the comet the way you would expect. When you run, your hair blows back behind you. A comet does not act like that. Its tail always points away from the sun, no matter which direction the comet is moving. Watch a comet fall toward the sun, and its tail streams out behind it, away from the sun. Fair enough. But then the comet whips around the sun and races back out toward deep space. Now the tail swings all the way around and leads the comet, still pointing away from the sun, streaming out in front like headlights on a car driving backward. Something near the sun was blowing that tail outward. Some invisible force poured off the sun in every direction and shoved the comet's dust away. Astronomers could see the effect for centuries before anyone could name the cause. It was one of the oldest unsolved puzzles hanging in plain sight. Some guessed it was a wind of particles from the sun, and part of the answer really is a stream of particles we now call the solar wind. But there was a second pusher, and it was pure light. The sun's own glow was pressing on the tiny grains of dust, driving them away, exactly as Maxwell's equations promised. Sunlight was strong enough to blow the dust of a comet across the sky. This is the strange thing about light pressure. On your hand, it is nothing. On a heavy object, it is nothing. But dust grains are unbelievably tiny and light. For a speck of comet dust floating in space with almost no weight to hold it in place, the gentle push of sunlight is like a hurricane. The smaller and lighter the object, the more that faint push matters. A boulder ignores sunlight. A dust grain gets swept away like a leaf in a gale. So the comet's tail was proof, written across the heavens, that light can move matter. It had been there all along, glowing over ancient cities, painted on cave walls, feared as an omen. Nobody knew they were staring at Maxwell's prediction come to life, thousands of years before Maxwell was born. But a tail in the sky is far away and hard to test. You cannot bring a comet into a lab. To truly prove that light pushes, someone had to catch the force with their own hands, on a table, in a sealed jar. And catching a force lighter than a shadow turned out to be brutally hard. The man who caught it was Pyotr Lebedev, and his enemy was air. Lebedev worked in Russia at the turn of the 20th century. He set out to do what nobody had managed, to measure the push of light on a table and prove Maxwell right with a real machine. The trouble was every force in the room was bigger than the one he wanted. Light's push is tiny. But when light hits an object, it also warms it. A warm object heats the air touching it, and hot air swirls and shoves far harder than the light ever could. So the moment Lebedev shined a beam on anything, the heat effects blew his measurement to pieces. It was like trying to weigh a feather during an earthquake. His answer was to remove the air. He built a sealed glass chamber and pumped out as much air as the tools of his day allowed, creating a near vacuum. With almost no air left, there was almost no swirling hot air to ruin things. What remained was the pure, naked push of light. Inside the chamber he hung a delicate contraption. Picture a tiny set of thin metal wings, light as paper, dangling from a thread so fine it was almost invisible. This was a torsion balance, a way to catch forces far too weak for any scale. If the wings turned even a hair, the thread would twist, and by watching the twist he could measure a force lighter than a breath. Then he aimed a bright beam of light at the little wings, They moved. The wings turned, the thread twisted, and Lebedev watched light push on the solid metal with his own eyes. He measured the size of the shove, and it matched Maxwell's prediction. The number the equations had promised decades earlier came true on his table. This was a triumph that took years of maddening work. Lebedev had to rule out every other explanation. Was it heat? He redesigned the experiment to cancel heat. Was it leftover air? He pumped harder and tested again. One by one, he closed every loophole until only one answer remained. Light, and light alone, was doing the pushing. The force he caught was staggeringly small. The push of a strong beam on his little wings was about the same as the weight of a few specks of dust. He had built one of the most sensitive machines of his age to catch something that faint, and he had won. Maxwell was finally proven right, 30 years after he first predicted it. Light pushes on matter. It was no longer ink on a page or a comet far away. It was a fact, measured in a lab, repeatable by anyone with the patience and skill to fight off the air. The mystery of the pushing light was solved at the level of proof. Light presses on everything. But the deeper question, the how, was still murky. Lebedev showed that it happens. He could not fully explain why a wave of energy carries a punch at all. His machine caught the effect and left the reason floating just out of reach. The real reason lives inside one short equation, a piece of math that ties energy and momentum together without any mass in sight. Once you see it, the whole mystery clicks into place, and you understand how nothing can shove something after all. The heart of the whole puzzle fits in a single line of math, and you do not need to be a genius to feel what it means. For everyday objects, the punch of a moving thing comes from mass times speed. Heavy and fast means a big punch. That rule runs your whole world from car crashes to baseball. It fooled scientists for centuries into thinking mass was required for momentum. But that rule is only a special case of a deeper one. The deeper rule, which Maxwell's work pointed toward and Einstein later nailed down, says that momentum can also come straight from energy, as long as that energy is racing at the speed of light. Divide the energy of a beam by the speed of light, and you get its momentum. No mass appears in that math anywhere. Read that again, slowly. The punch of light depends on how much energy it carries and how fast it moves. Light carries plenty of energy, and it moves at the fastest speed there is. So it has a real punch, built purely from energy, with mass left out of the picture entirely. Here is a way to picture it. Imagine energy and momentum as two sides of the same coin whenever something moves near light speed. You cannot have one without the other. A beam of light is energy in flight, so it automatically drags a bit of momentum along with it, like a shadow that always follows a walker. Where the energy goes, the punch goes too. This is why the old law seemed broken, but never was. Mass times speed is not the true source of momentum. It is a shortcut that happens to work for slow, heavy things. The true source is deeper, and it welcomes anything that moves, mass or no mass. Light qualifies. Light moves, so light carries a punch. Now the comet tail makes sense. Sunlight carries energy, so it carries momentum, so it shoves the dust. Lebedev's wings make sense too. The beam handed its momentum to the metal, and the metal turned. Every mystery so far bows to this one small equation, and it hands us a gift. Because the momentum of light is just its energy divided by that giant speed number, we can predict the push in any situation. Shine more energy, and you get more push. That is the entire secret behind light sails, laser tractors, and every machine we're about to meet. Pour in enough light energy, and the tiny push stacks up into something that can move a spaceship. There is one more twist that makes the push stronger. When light hits a black, dull surface, the surface soaks up the beam and gets 1 unit of push. But when light hits a mirror, it bounces straight back the way it came. A bouncing beam hands over twice the punch because it has to stop, turn around and leave, and each of those steps costs momentum. So a shiny mirror feels double the shove of a black wall. That doubling is why every real light sail is a mirror. Engineers want every last scrap of push so they make their sails shine. We now have the full answer to our opening question. Light with no mass can move matter, because it carries momentum made of pure energy, and a mirror doubles the effect. The mystery is solved on paper. But paper is one thing. To really believe it We need to watch a single particle of light punch a single particle of matter, one-on-one, like two balls on a pool table. To see light punch matter one-on-one, we have to shrink our view down to a single particle of light. Light is a wave, as Maxwell showed, but light is also something else, something that sounds impossible at first. Light comes in tiny packets, little bullets of energy called photons. A photon is the smallest possible piece of light. Turn a dimmer switch down as low as it goes, and eventually you would be releasing photons one at a time, single grains of light leaving the bulb. Each photon has no mass, not almost no mass, exactly zero, and yet each photon carries a set amount of energy, and therefore a set amount of momentum following that same equation from before. A single photon is a massless bullet with a real punch packed inside it. This is the strangest idea we have met so far, so let me be honest about it. A photon is both a wave and a bullet at the same time. It spreads out like a ripple, and it also arrives in one tiny lump, like a single raindrop. Scientists spent decades fighting over this before accepting that light simply is both, depending on how you look at it. This is confirmed by countless experiments, not a guess. For now, think of the bullet side. A photon flies through space at light speed, carrying its little parcel of momentum. When it strikes something and stops, it has to dump that momentum somewhere. It hands the punch to whatever it hit. One photon delivers one tiny kick. A single kick is unimaginably small. But the sun fires out an ocean of photons. Sunlight pouring onto a sunny field drops trillions upon trillions of photons every second onto every square inch. Each one lands its microscopic punch. Add up that flood of tiny kicks, and you get a steady, gentle pressure pressing on everything in the light. Picture standing in a hailstorm where each hailstone weighs almost nothing. One stone you would never feel, but a blizzard of them, hour after hour, adds up to a real force leaning against you. Sunlight is exactly that, a blizzard of weightless bullets, each landing a punch too small to notice, together strong enough to blow a comet's tail across the sky. This picture also explains the mirror trick from before. A photon that gets absorbed by a black wall stops dead and hands over one kick. A photon that bounces off a mirror comes in, reverses, and flies back out. To reverse, it must first cancel its forward motion, then build up backward motion, which costs 2 kicks worth of momentum handed to the mirror, so mirrors get double the push. Same reason as before, now seen one bullet at a time. Once you see light as a stream of tiny bullets, the whole idea of light pushing matter stops feeling magical and starts feeling obvious. Of course, a stream of bullets pushes a wall. The only surprise is that these bullets weigh nothing at all and still land a punch. But here is where a good scientist gets suspicious. It is easy to imagine bullets pushing things. It is harder to prove that light really acts like a bullet in a true collision. Talk is cheap. We need to catch a single photon slamming into a single particle of matter and watch them ricochet, like two balls cracking together on a pool table. That is exactly what one scientist managed to do, and what he saw won him a place in every physics book ever written. His name was Arthur Compton, and he set up the ultimate test. He wanted to fire light at a single particle and watch them bounce like billiard balls. Compton worked in the 1920s. He took a beam of X-rays, which are just light with far more energy than the light your eyes can see, and aimed it at electrons. An electron is one of the tiny particles inside every atom, part of the fuzzy cloud that surrounds the core. It has a truly tiny mass, but unlike a photon, it is not zero. If light were only a smooth wave, one thing should happen when it hits an electron. The wave should shake the electron and bounce off with the same energy it came in with, its colour unchanged. That was the old prediction, and for gentle light it even seemed to hold. But Compton saw something the wave idea could not explain. When his X-ray photons bounced off electrons, they came away weaker, with less energy, and their colour shifted. The photon left the collision changed, drained of some of its punch, and the electron it hit went flying off, freshly kicked into motion. This was the pool table come to life. On a pool table, when the cue ball strikes another ball, the cue ball slows down and the struck ball speeds off. Energy and momentum split between them, following exact rules. Compton found that photons and electrons obey those very same rules. The photon is the cue ball. The electron is the ball it strikes. After the hit, the photon is slower and weaker, and the electron races away with the momentum it just received. Compton measured everything. The angle the photon bounced, the energy it lost, the speed the electron gained, and every number matched the prediction you get by treating the photon as a tiny bullet carrying real momentum, colliding by the same laws that govern billiard balls, not roughly, exactly. This was proof at the deepest level. Light does not just vaguely press on matter. A single photon carries a definite punch and hands it over in a clean collision, obeying the same momentum rules as any solid object. The massless bullet is real. It behaves like a ball with a punch, even though it weighs nothing and travels at the speed of light. The discovery was so important it earned Compton the Nobel Prize. It settled the argument for good. Light is made of particles that carry momentum, and those particles collide with matter by ordinary collision rules. Everything Maxwell predicted, everything Lebedev measured, now had a rock-solid foundation at the level of a single particle. So here we stand, with the mystery fully cracked. Light has no mass. Light carries momentum built from pure energy. That momentum is real, measurable, and delivered by tiny bullets called photons, one clean kick at a time. Nothing can push something because that nothing is a river of weightless bullets, each landing a punch. The science is settled. Now the real fun begins, because once humans understood that light pushes, they started asking a wild question. If light can shove an electron, and shove a comet's dust, and shove Lebedev's little wings, then how big a thing could we push if we tried hard enough? Could we push a machine, a spacecraft, a person? Before we sail off on beams of light, we have to clear up one famous trick that has fooled people for over a century, a little spinning toy that seems to prove light pushes, and actually proves the opposite. Walk into a science museum or an old curiosity shop and you might spot it. A little glass bulb with a tiny windmill inside. The windmill has 4 vanes, each one black on one side and shiny on the other. Set it in sunlight and it spins, faster and faster, turning all by itself. It looks like a toy powered by pure light. This gadget is called a Crookes radiometer, invented by William Crookes in the 1870s. When people first saw it spin in the sun, they thought they were watching light pressure with their own eyes. Light hits the vanes, light pushes the vanes, the wheel turns. Simple, beautiful, wrong. Here is the first clue that something is off. Watch which way it spins. Light should push hardest on the shiny mirror sides, because mirrors get double the punch, remember? So the shiny sides should be shoved backward and the black sides should lead. But the radiometer spins the other way. The black sides move backward, as if they are being pushed harder than the mirrors. That is the opposite of what real light pressure would do. So the spinning toy that seems to prove light pressure is actually breaking the rule of light pressure. Something else is turning that wheel, something stronger than light. And for years, the greatest scientists of the age argued about what it was. Even Maxwell weighed in. The puzzle was tougher than it looked. The answer lives in the air. A Crookes radiometer is not a perfect vacuum. A little bit of air is left inside on purpose, and that leftover air is the key. The black side of each vane soaks up light and heats up. The shiny side reflects light and stays cooler. So one side of every vane is warm and the other side is cool. Now think about the air molecules bouncing off those vanes. Molecules that hit the hot black side pick up extra energy and bounce away faster and harder. Molecules hitting the cool shiny side bounce away gently. The hard-hitting molecules on the black side shove the vane more than the gentle ones on the shiny side. So the black side gets pushed away and the wheel spins with the black sides retreating. The radiometer spins because of warm air, not because of light. Light heats the vanes, but air does the pushing. The whole thing is a heat engine in disguise, driven by molecules drumming harder on the hot side than the cold side. This is confirmed and well understood today, though it took decades to sort out. Real light pressure is far too weak to spin that little wheel against the drag of the leftover air. If you pumped out all the air to make a true vacuum, the radiometer would stop responding the way people expect. The air is doing the heavy lifting. This little toy carries a big lesson. Light pressure is so faint that on Earth, surrounded by air and heat, it almost always hides behind stronger forces. Warm air beats it. A breath of wind beats it. This is the exact same trouble that nearly defeated Lebedev, and it is why catching pure light pressure took such heroic care. Which raises a hard question. If light pressure loses to a whisper of warm air, how could it ever push something as heavy as a spacecraft? The answer is that you have to leave Earth behind, go where there is no air, and give the light room to work. On Earth, light pressure barely stands a chance. Now we understand why. Air gets in the way, heat gets in the way, gravity pins everything down with a grip billions of times stronger than any beam. Think about how weak the push really is down here. The sunlight landing on your entire backyard, every photon of it, adds up to a force smaller than the weight of a paperclip. Gravity, meanwhile, is holding down every blade of grass, every pebble, your whole body, with a force you fight just by standing up. In a contest between sunlight and gravity on the ground, sunlight loses instantly, every time. Add in the air, and it gets worse. Any object sitting in sunlight warms up, heats the air around it, and stirs up breezes far stronger than the light's push. The radiometer taught us that. Down here, light pressure is the weakest kid on the playground, shoved aside by gravity, air, heat, and the faintest draft. So for most of human history, light pressure seemed like a curiosity and nothing more. A real effect, proven in a lab but useless. A force too feeble to lift a feather. What could you possibly do with a push that loses to a paperclip? The trick is to change the playing field. Everything that beats light pressure on Earth vanishes in space. Out beyond our atmosphere there is no air, so no breezes and no heat drag. And far from any planet, gravity spreads thin and loosens its grip. Suddenly the weakest kid on the playground is the only kid on the playground. There is one more secret weapon in space. Time. On Earth, if a force cannot move something in a few seconds, we call it useless. But a spacecraft drifting through space has all the time in the world. A push too weak to notice in a second becomes powerful when it acts every second for months or years, without ever stopping. This is the part people miss about light pressure. It never quits. A rocket burns its fuel in minutes and then coasts, its engine dead. But sunlight keeps pushing for as long as the sun shines, which is to say, forever, from any human point of view. A push that is tiny but endless will eventually beat a push that is huge but brief. Picture two ways to move a heavy cart. One person gives it a single mighty shove and walks away. Another person leans against it with one finger and never stops leaning day after day. At first, the mighty shove wins easily, but give it enough time, and the endless finger push builds up more and more speed, faster than the cart ever went from the single shove. In space, light is the endless finger, and it never gets tired. So the plan becomes clear. Take light pressure off the crowded, heavy, windy playground of Earth. Put it in the empty silence of space, give it a big shiny sail to push against, and let it push without stopping for months on end. A force that loses to a paperclip on Earth could, out there, carry a ship to unimaginable speed. For centuries this was only a dream in the minds of a few bold thinkers. Then engineers actually built the sails, folded them onto rockets, and flung them into orbit to see if sunshine could truly move a machine. The idea has a beautiful name. A solar sail, a ship that sails on sunlight. The concept copies the oldest technology on the sea. For thousands of years, sailing ships crossed oceans using nothing but wind. A sail catches the wind pushes the sail, the ship moves. No engine, no fuel, just a big sheet held up to catch a push that costs nothing. A solar sail does the same thing with light instead of wind. You unfold an enormous, ultra-thin, mirror-bright sheet in space. Sunlight strikes it, and each photon hands over its tiny punch. Trillions of photons drum against the mirror every second, and their combined push nudges the ship forward. No engine, no fuel, just a big shiny sheet held up to catch the push of the sun. The difference is the sheer size needed. Wind is thick and heavy, so ocean sails can be modest. Light pressure is feather faint, so a solar sail has to be huge and impossibly light to catch enough push to matter. Real solar sails are made of material thinner than a trash bag, sometimes only a few times thicker than a soap bubble, stretched across an area as big as a boxing ring or larger. Here is why fuel-free travel is such a giant deal. Every normal rocket faces a cruel problem. To go fast, it needs fuel, but fuel is heavy, so it needs more fuel just to carry the fuel, and more fuel to carry that. A rocket sailing to the outer planets is mostly a giant fuel tank with a tiny ship on top. Almost all the weight is fuel that gets burned and thrown away in the first few minutes. A solar sail carries no fuel at all. Its engine is the sun, and the sun stays behind, pouring out free light forever. The sail just keeps catching that light and keeps speeding up. It starts slow, painfully slow, adding only a whisper of speed each second. But it never stops adding. Day after day, month after month, the speed piles up. Run the numbers over a long trip and the results get wild. A solar sail that starts out crawling can, after a year or two of endless gentle push, be flying faster than any rocket we have ever built. It beats the rocket the same way the endless finger beats the single shove. Slow and steady forever wins the race across the solar system. There is a catch, and it points back toward the sun. Light pressure gets stronger the closer you are to the sun, where the light is brightest, and weaker as you drift out toward the cold edge of the solar system, where sunlight thins to a trickle. So a solar sail works best near the sun and struggles in the dark far reaches. Sailors of the future would plan their voyages around the sun the way old sailors planned around the wind. For decades, the solar sail was only an idea sketched by dreamers and scientists. Everyone agreed the physics worked. Light pushes, and a big enough mirror would catch enough push to sail, but nobody had ever unfurled a real one in space and proven it could fly. Plenty of things work perfectly on paper and fail the moment they leave the ground. Then, in the year 2010, a Japanese spacecraft folded up a shining sail, rode a rocket into space, and got ready to unfurl the first true sailing ship of the stars. The spacecraft was called Ikaros, and it was a gamble. Japan's space agency built it to answer one question once and for all. Could a solar sail really fly on sunlight alone, out in real space far from any lab? They named it after Icarus, the boy from the old Greek story who flew toward the sun. This time, the sun would be the friend, not the danger. Ikaros launched in the year 2010. Tucked inside was a sail folded up tight, because a sail big enough to catch sunlight is far too large to launch open. It has to ride to space packed small, then bloom outward once it arrives, like a flower opening in slow motion. Unfolding that sail was the terrifying part. The sheet was about 46 feet across on each side, roughly the width of a basketball court, yet thinner than a human hair. It had to spread out flat and smooth without tearing, tangling, or ripping. To do it, the spacecraft spun in place, and the spinning flung the folded sail outward, using the spin to pull it taut like a skater's arms swinging out. Slowly, carefully, the giant square unfurled and stretched tight. It worked. Ikaros spread its shining sail in open space, the first spacecraft ever to do so. And then came the real test. Would sunlight actually push it? The scientists watched the spacecraft's motion with extreme care, and there it was. Ikaros was speeding up, ever so slightly, pushed by nothing but the light of the sun striking its sail. They measured the push and confirmed it came from sunlight, exactly as Maxwell's old equations promised. A ship was sailing on light for real, out among the planets. The push was gentle almost beyond belief. The force of sunlight on that entire basketball court-sized sail was about the weight of a small paperclip resting in your hand. That is the whole engine. A paperclip of push, driving a spacecraft across space. But remember the lesson. That push never stopped, and over time it added real speed. Ikaros did more than just drift. Its team could tilt the sail, changing the angle it met the sunlight, and steer the craft. By turning the sail like a captain turning a real sail into the wind, they nudged the spacecraft's path this way and that. This proved you could not only sail on light, but actually navigate with it, aiming your ship wherever you wanted to go. The little sailing ship cruised past Venus and kept going, sailing deeper into space, driven the whole way by the steady hand of sunlight. It turned a century of theory into a working machine. Every physicist from Maxwell to Compton had been building toward this moment, and Icaros proved them all right in the most beautiful way, by simply sailing away. This changed everything about how we think of travel between worlds. A ship that needs no fuel could, in theory, keep going forever, refueling on sunlight every second of the trip. The oceans of space suddenly had a wind to sail on, but Icaros flew far from home, hard for most people to see or cheer. A group of space fans wanted to do something bolder and closer, to launch a sail that ordinary people could watch climb higher in the sky, pushed by a light right above their own heads. The group was the Planetary Society, and their sail had a job to prove that was even harder than just flying. Icaros had shown a sail could speed up on sunlight far from Earth, but the Planetary Society, a group of space lovers led for years by famous scientists, wanted to answer a tougher question. Could a solar sail actually climb, using sunlight to raise its own orbit higher above the Earth, fighting against the planet's pull? Their spacecraft was called LightSail 2, and it launched in the year 2019. It was small, about the size of a loaf of bread when folded, one of those tiny satellites you could hold in two hands. Packed inside was a sail that would open to about the size of a boxing ring, made of shining material thinner than the plastic wrap in your kitchen. Once in orbit around Earth, LightSail 2 popped open its 4 booms and stretched the sail flat. Now the hard part began. The spacecraft was circling the Earth, and it wanted to use sunlight to push itself into a higher orbit, farther from the planet. This meant catching the sun's push on the right side of every orbit, and turning the sail edge on when the push would work against it. Picture pushing a child on a swing. If you shove at the right moment each time, the swing goes higher and higher. Push at the wrong moment and you kill the motion. LightSail 2 had to do the same trick with its sail, turning the shiny face to the sun on the helpful half of each orbit, then twisting edge on during the unhelpful half, over and over, thousands of times. It worked. Over several days, LightSail 2 slowly raised the high point of its orbit by about 1.25 miles, lifting itself higher above the Earth using sunlight alone. A tiny spacecraft the size of a bread loaf had climbed against the pull of an entire planet, powered by nothing but a stream of weightless photons striking a shiny sheet. The push was, once again, featherlight. The sunlight on that whole boxing ring-sized sail pressed with a force smaller than the weight of a housefly. But by timing it perfectly, orbit after orbit, that housefly of push lifted the spacecraft higher into the sky. There was a fight going on the whole time, and it reveals how close to the edge this technology runs. LightSail 2 orbited fairly low, where a few thin wisps of the atmosphere still reached. That trace of air dragged on the sail and tried to pull the craft back down. So the sunlight was pushing the ship up, while the last whispers of air were dragging it down, a tug of war between light and air playing out miles above the ground. Eventually the air drag won, as everyone knew it would, and LightSail 2 slowly spiraled back down after finishing its mission. But it had already made its point. Sunlight could lift a spacecraft against gravity. A sail could be a real engine, climbing the sky on light. These sails were triumphs, and they were also baby steps. Icaros and LightSail 2 moved slowly, gaining speed like a snail. That is fine for cruising around our own solar system, but some dreamers were staring much farther out, at the stars themselves, and they wanted to know if light could push a ship not just faster, but unimaginably faster, fast enough to leave the sun entirely behind. The stars are the ultimate prize, and they are cruelly far away. The nearest star to our sun, other than the sun itself, is a small red dot called Proxima Centauri. It is so far that light from it, moving at the fastest speed there is, takes more than 4 years to reach us. Our fastest spacecraft ever built, if aimed at that star, would take tens of thousands of years to arrive. Whole civilizations would rise and fall before it got there. That distance has always seemed like a locked door. The stars are simply too far. No rocket can carry enough fuel to cross that gulf in a human lifetime, or even 100 human lifetimes. For most of history, travel to another star lived only in stories. Then a group of scientists and dreamers launched a bold plan called Breakthrough Starshot. backed by wealthy supporters and famous physicists, including some of the greatest minds alive. Their idea was wild, and it was built entirely on the push of light. Here is their thinking. A big solar sail near the sun catches sunlight and speeds up slowly, because sunlight, spread across all of space, is fairly weak. But what if you did not rely on the sun at all? What if you built a gigantic laser on Earth and aimed a blindingly intense beam at a sail, pouring far more light energy onto it than the sun ever could? A laser can be made stunningly powerful and focused into a tight beam. Point that beam at a shiny sail and the push jumps up enormously, far beyond what plain sunlight gives. Instead of a paperclip of force-building speed over months, you could deliver a hard, fierce shove concentrated into a few short minutes. But there is a problem. A laser strong enough to push a normal spacecraft would need to be impossibly huge, so Starshot flips the plan. Do not push something heavy, push something almost weightless. Make the spacecraft tiny, a little chip the size of a postage stamp, packed with cameras and sensors, attached to a small sail as thin as a soap film, something so light that even a laser push can fling it forward at incredible speed. The plan is to fire a massive laser array from the ground at this tiny sail for just a few minutes. In those few minutes, the beam would slam the little chip up to a speed no human object has ever reached, a fifth of the speed of light. That is thousands of times faster than any rocket, fast enough to cross the distance from Earth to the Moon in seconds. At that blistering speed, the tiny chip could reach Proxima Centauri in about 20 years instead of tens of thousands. A journey that once seemed to need a whole ice age could shrink to a single human career. A person could launch it as a young scientist and still be alive to see the pictures come home. This is confirmed to be the goal, though the machine does not yet exist. The lasers needed are far beyond anything built today, and countless hard problems remain unsolved. It is a dream with real physics under it, chasing a star with a beam of light. To believe it could ever work, we have to look closer at that stunning claim, a spacecraft riding light to a fifth of the speed of light, never burning a single drop of fuel, a fifth of the speed of light. Let that number sink into your imagination, because it is almost too big to hold. Light travels about 186,000 miles every second. A fifth of that is around 37,000 miles per second. At that speed, you could circle the entire Earth in less time than it takes to read this sentence. You could cross from New York to Los Angeles in about a tenth of a second. The fastest rifle bullet ever fired would look frozen in place next to this little chip. Now here is the part that should stop you cold. The tiny Starshot craft would reach that unthinkable speed carrying no fuel at all. Not a drop. Its entire push comes from light striking a sail, delivered by a laser sitting safely back on Earth. All the energy stays home. Only the feather-light chip flies away riding the beam. This is the deepest gift of light pressure, taken to its extreme. A rocket must haul its own fuel, which is why rockets are mostly giant fuel tanks. A light sail leaves its engine behind entirely. The laser is the engine. The sail is just the thing that catches the push. Separate the engine from the ship, and suddenly the ship can be almost nothing, which means it can go almost impossibly fast. Think again about the endless finger versus the single shove. Starshot is neither. It is a brutal, concentrated slam, a laser dumping enormous energy onto a nearly weightless sail in a few short minutes. Because the sail weighs so little, the energy translates into staggering speed. Push a feather hard enough and it flies like a bullet. Push a chip on a soap film sail with a laser and it flies like a piece of starlight. The speed matters for one reason above all: distance. The stars are so far away that ordinary speeds turn any trip into a journey of tens of thousands of years. Only by reaching a real fraction of light speed does a star become reachable within a human lifetime. Light pressure is the one known way to get there without inventing brand new physics. It uses forces we already understand, proven by Maxwell, Lebedev and Compton, just pushed to their limit. There are monstrous problems, and honesty demands naming them. A speck of space dust hitting a craft moving that fast would strike like a bomb. Aiming a laser precisely at a sail already racing away is fiendishly hard. Building a laser that powerful may take decades or longer, and once the chip flies past its target star in a blink, it cannot slow down or stop. It would snap a few pictures during a lightning-fast flyby and beam them home across years of empty space. All of this is real, and none of it is solved. But the core idea rests on solid ground. Light carries momentum. A mirror doubles the push. Pour enough light onto a light enough sail, and you can reach a fifth of the speed of light. The physics says yes, the engineering says not yet. That gap between yes and not yet is where the future of star travel is being fought out right now. Whether we ever reach the stars this way is still an open question, but light pressure has already conquered something closer to home and just as astonishing. It can reach out and grab a single living cell, lift it, and hold it in mid-air using nothing but a focused beam. Push is only half the story. It turns out light can also grab. So far we have seen light shove things away, driving comet dust outward, pushing sails forward, blasting chips toward the stars. Everything has been a push, a force pointing away from the light source, so it sounds impossible that light could ever pull an object toward itself, or hold it still, or lift it. Yet that is exactly what scientists learned to do, and it opened a whole new world. The tool is called optical tweezers. The name fits perfectly. These are tweezers made of light, able to pick up and hold objects far too small for any real tweezers to touch. Not metal pincers, but a beam so cleverly shaped that it can trap a tiny particle in its grip and move it around like a claw in an arcade machine. Here is how something so strange can work. When you take a laser beam and focus it down to an incredibly tight point using a lens, the light near that focus is not even in strength. It is brightest right at the centre and fades toward the edges, and a tiny transparent object like a plastic bead or a living cell bends the light passing through it, the way a magnifying glass bends sunlight. Because the object bends the light, and because the light pushes back whenever it bends, the object gets nudged toward the brightest spot at the centre of the focus. If it drifts left, the light pushes it right, back to centre. If it drifts up, the light pushes it down, back to centre. From every direction, the beam gently herds the particle toward the middle and holds it there, trapped in a cage made of light. Picture a marble sitting at the bottom of a smooth bowl. No matter which way it rolls, it slides back to the lowest point in the middle. The focused laser makes an invisible bowl of light, and the little particle settles into the bottom of it, held in place, floating in the beam. Move the beam, and the bowl moves, and the particle rides along inside it. This is real and works right now in labs all over the world. Scientists use optical tweezers every single day, and the objects they hold are astonishing. They can trap a single bacterium without crushing it. They can grab one living cell, hold it in midair, and even move it around, all without any solid object ever touching it. The only thing touching the cell is light. Think about how gentle and precise that is. A living cell is softer and more delicate than almost anything. Poke it with a needle and it might die. But a beam of light can cradle it, lift it, and set it down somewhere else, as softly as catching a soap bubble. The same force that blows a comet's tail across the sky can hold a single living cell as tenderly as a hand cupping water. Scientists use this to study the tiny machines inside our bodies. They can grab the two ends of a single strand of DNA, the code of life, and gently pull to measure how strong it is. They can watch the little motors inside cells at work. Light became a pair of hands small enough to touch the building blocks of life itself. The scientist who first figured out how to trap matter with light spent years being doubted and eventually won the highest prize in science for it. His story is one of patience, stubbornness, and a very long wait. His name was Arthur Ashkin, and the world made him wait a very long time. Ashkin worked at a famous research lab in the United States, and back in the 1970s he became fascinated by a simple question. Everyone knew light could push things, but could you use light not just to shove, but to grab and hold? Could you build a trap out of pure light? He started experimenting with tiny transparent beads and laser beams. Bit by bit he discovered the trick we just described. A tightly focused beam creates a spot that pulls small objects into its centre and holds them. He had invented the optical trap, the tweezers made of light. He could catch a tiny bead in a beam and hold it floating, suspended in nothing but light. Then he pushed further, and this is where it got beautiful. Ashkin wondered if he could trap living things without killing them. Lasers can burn, so this was risky. He experimented carefully, and he found he could catch living cells and even hold tiny organisms, holding them alive and unharmed in his beam of light. He could reach into a drop of water with light and pick up a single living thing. This was a stunning achievement. It gave biologists a magical new tool, a way to touch and move the smallest living pieces of nature without damaging them. Over the years that followed, optical tweezers spread into laboratories everywhere and unlocked discovery after discovery about how life works at its tiniest scale. Here is the part that makes his story so human. Ashkin made these breakthroughs in the 1970s and 80s. The world took its time to understand how important they were. Recognition came slowly, over decades, and the highest honour in science, the Nobel Prize, did not arrive until the year 2018. By then, Arthur Ashkin was 96 years old. He had waited more than 40 years. When they announced his prize, he became the oldest person ever to win a Nobel at that time. Reporters called his home to congratulate him, and he was reportedly too busy in his lab working on his next project to spend much time celebrating. 40 years of patience, and he was still at the bench, still curious, still working. His life carries a quiet lesson about science. A discovery can be brilliant and still wait decades to be understood. The person who first sees something true may be grey-haired before the world catches up. Ashkin trusted his beams of light long before anyone handed him a prize for them, and he kept working whether the world was watching or not. His invention traces straight back through everything we have learned. Light carries momentum. That momentum can push a particle toward a bright spot instead of just away. Focus the light cleverly, and the push becomes a grip. The same physics that Maxwell wrote down and Lebedev measured, bent to a new purpose, became a hand made of light that could hold the stuff of life. Ashkin had learned to trap and hold particles with light, but other scientists were chasing something that sounds even stranger. They wanted to use light not to hold atoms still in a beam, but to slow them down, to cool them, to chill matter to the coldest temperatures anywhere in the universe, using nothing but carefully aimed light. To understand the next trick, you need to know a secret about temperature. Heat is really just motion. When something is hot, its atoms are jiggling and racing around fast. When something is cold, its atoms are moving slowly. Temperature is nothing more than a measure of how fast the tiny particles inside something are moving. Fast means hot, slow means cold. To cool something down, you have to slow its atoms. Now here is the amazing idea. If light can push atoms, then maybe light can be aimed to push against their motion, slowing them down. And if you slow the atoms, you cool the substance. Scientists realized they might be able to use beams of light as brakes, gently stopping atoms in their tracks. They called it laser cooling. Picture an atom flying toward a laser beam. The scientists tune the light just right so that the atom, rushing toward the light, absorbs photons head-on. Each photon it absorbs gives it a tiny kick backward, against its motion, like tiny bullets striking the front of a speeding car. One photon barely matters, but an atom can absorb and spit out millions of photons every second, taking millions of little backward kicks, and that slows it down fast. The clever part is making sure the light only pushes back on atoms that are moving toward it, so the beam always acts as a brake and never a gas pedal. Scientists surround the atoms with laser beams coming from every direction. No matter which way an atom tries to move, a beam is there to push it back. The atoms get trapped in a crisscross of light, slowing more and more like a swarm of bees caught in thick honey. As the atoms slow, they cool, and laser cooling can slow atoms almost to a complete stop, which means it can chill them to almost the coldest temperature possible, a temperature scientists call absolute zero, where motion nearly ceases entirely. These are the coldest spots anywhere that we know of, colder than the deepest depths of outer space. This is confirmed, real, everyday science now, though it sounded impossible when first proposed, cooling atoms with light of all things, when light usually warms things up. It seems backward, using light to make the coldest place in the universe, but it follows directly from everything we have learned. Photons carry momentum, aim them against an atom's motion, and they push it to a halt. A halted atom is a frozen atom. The temperatures reached are almost impossible to imagine. We are talking about matter chilled to a tiny fraction of a degree above absolute zero, the coldest anything can ever be. In a small chamber on a lab table, scientists create a cold deeper than the Kong empty space between the stars, using beams of light as their refrigerator. This might sound like a mere curiosity, a party trick for physicists. It is far more. When atoms get that cold and that slow, they start behaving in bizarre new ways, revealing hidden rules of nature that stay invisible at normal temperatures, and ultra-cold atoms power some of the most precise clocks and sensors humanity has ever built. The strangeness of supercold matter is a story of its own. But the real jaw-dropper is just how cold we're talking about, a cold so extreme it beats the frozen void of deep space itself, made by light, right here on Earth. Space is famously cold. Empty space, far from any star, sits at hundreds of degrees below zero. It is one of the coldest things most people can imagine, a frozen darkness where any warmth quickly bleeds away. Surely nothing could be colder than the deep void between the stars. Something can. In laboratories on Earth, scientists using laser cooling create matter far colder than empty space. Much, much colder. The gap is not small, it is enormous. Let me put the two side by side. The cold of deep space is around 450 degrees below zero on the Fahrenheit scale, close to the coldest natural temperature anywhere. That is bitter beyond anything humans could survive for an instant. Yet laser-cooled atoms in a lab reach temperatures 1,000 times closer to the true bottom, absolute zero, than the void of space ever gets. The lab beats space by a landslide. How can a warm room on Earth hold something colder than the frozen gulf between the stars? Because deep space, cold as it is, still has a faint background glow left over from the birth of the universe, a whisper of warmth that keeps it from reaching the true bottom. Space cannot fully cool itself, but in a lab, with lasers precisely breaking every atom, scientists can strip away almost all motion and dive far below what nature manages on its own. Think about what that means. The coldest place we know of in the entire universe is not floating somewhere in distant space. It is on Earth, inside a machine, made by people using beams of light. We took the same force that blows comet tails and pushes solar sails, and used it to build the ultimate deep freeze, colder than the darkness between galaxies. And down at those unthinkable temperatures, matter changes. When atoms are chilled to nearly absolute zero and slowed to almost a standstill, they can lose their separate identities and blur together into a single shared state, all acting as one. Thousands of atoms stop behaving like a crowd and start behaving like a single object, moving in perfect step. This is a genuinely new form of matter, one that does not exist anywhere in the warm, ordinary world. Scientists call this ultra-cold matter by special names, and they study it to uncover deep secrets of how the universe works at its most basic level. Rules of nature that hide behind the noise and jiggle of the normal temperatures suddenly stand out clearly when everything goes still and cold. The deep freeze made of light became a window into the hidden machinery of reality. There is a beautiful circle in all of this. Light usually adds energy and warms things up. A campfire, a sunbeam, a light bulb, all of them heat what they touch. Yet with enough cleverness, that same light became the coldest force we command, capable of freezing atoms almost solid. The push of light works both ways, speeding atoms up or breaking them to a crawl, depending only on how you aim it. From pushing sails between planets to freezing atoms colder than space, light pressure keeps surprising us, and we have been living entirely inside the human scale, machines and labs and spacecraft. But light pressure also shapes things far bigger, on a scale that dwarfs anything people build. It quietly steers giant rocks tumbling through space, over spans of time so long they make a human life look like a single blink. Out in space float countless chunks of rock called asteroids, some as small as a house, some as large as a mountain. And sunlight, that feather light push, has been secretly steering them for billions of years, in a way nobody expected. You already know sunlight pushes on things directly. Light hits an asteroid and gives it a tiny shove away from the sun. But there is a second, sneakier way sunlight moves asteroids, and it is far stranger. It comes not from the light that lands, but from the heat that leaves. Here is how it works. An asteroid spins as it orbits the sun. The side facing the sun gets warm during its day. Then that warm side rotates around to the night side, and as it turns, it slowly gives off its heat, glowing faintly in infrared, the same warmth you feel radiating off pavement after sunset. That escaping heat is itself a form of light, and light, as we know by now, carries momentum. So when the warm side of the asteroid radiates its heat away, that heat leaves as a stream of photons, and those photons give the asteroid a tiny push in the opposite direction, like the world's gentlest rocket exhaust. The asteroid is slowly shoved by its own escaping warmth. This sneaky push is called the Yarkovsky effect, named after the engineer who first dreamed it up. The push is absurdly small. On any given day it does nothing you could measure, but asteroids drift through space for millions and billions of years, and the push never stops. Day after day, century after century, that faint warmth pushes always in roughly the same direction, and it slowly changes the asteroid's path around the Sun. Over millions of years, the effect can move an asteroid across huge stretches of space, nudging its orbit onto a whole new course. This is the endless finger again, working on a rock the size of a mountain across spans of time longer than humans have existed. A push too weak to notice, applied without pause for eons, quietly rewrites the journey of a giant stone. Scientists have confirmed this effect by tracking real asteroids and watching their orbits drift exactly as the Yarkovsky effect predicts. It is real, measured, and important. Why should you care about a rock being nudged in slow motion? Because some of those asteroids cross Earth's path. The Yarkovsky effect slowly steers asteroids around the solar system, and over long ages it can guide some of them toward orbits that bring them near our planet or away from us. This gentle warmth push helps decide which distant rocks might one day come knocking at Earth's door. Scientists who track dangerous asteroids have to account for the Yarkovsky effect in their calculations. When they predict where an asteroid will be 100 years from now, they cannot ignore this tiny heat push, because over a century it can shift the rock's position by a huge distance, enough to turn a near miss into a hit, or a hit into a near miss. A force lighter than a whisper becomes a matter of planetary life and death. That thought leads somewhere both frightening and hopeful. If sunlight's gentle warmth can steer an asteroid toward us over long ages, then maybe we could use that same gentle push, on purpose, to steer a dangerous asteroid away. Imagine astronomers spot a large asteroid on a collision course with Earth, still years away but heading straight for us. How would we stop it? Blowing it up, like in the movies, might just turn one big rock into many deadly ones. But there could be a gentler answer, one built on the whisper of light. We just learned that an asteroid's own escaping heat can push it, slowly reshaping its orbit over long ages. What if we could control that push? What if we could change how an asteroid soaks up and gives off heat, and use that to steer it off its deadly path, using sunlight as the engine? One idea is beautifully simple. Paint the asteroid. A dark surface soaks up more sunlight and radiates more heat, while a light surface reflects sunlight and stays cooler. If you change the colour of one side of an approaching asteroid, you would change how the sun's warmth pushes on it. Over years, that altered push could gently shift its path, moving the asteroid just enough to miss the Earth entirely. The key word is time. This gentle nudge would never work at the last minute. It is far too weak to shove a mountain aside in a hurry. But catch the asteroid years or decades before impact, and a tiny steady push, applied every single day, could slowly bend its course. Move the rock by the width of a hair each day, and over decades that adds up to moving it by a distance wider than the Earth. A miss by a whisker, earned one whisper at a time. Picture two cars aimed to crash far down a long road. You do not need to yank one violently aside. Nudge its steering wheel a hair right now, and by the time they reach the crash point, one car has drifted far off to the side and they pass safely. The earlier you nudge, the less force you need. An asteroid years away needs only the faintest steady push to miss us completely if we start soon enough. Scientists take this seriously, and related ideas are being studied and even tested in early forms. There are other ways to nudge an asteroid too, but many of the gentlest ideas lean on the same principle we have followed the whole way, the quiet, endless push tied to light and heat. The same force that blows a comet's tail could one day save every life on Earth. This flips the whole story on its head. We started with sunlight as a force too weak to feel, a curiosity that loses to a paperclip. Now that same force stands as a possible shield against the kind of asteroid strike that once wiped out the dinosaurs. The feeblest push in the solar system, given enough time, could be the thing that saves our species. That is the hidden power of a tiny force that never quits. It can doom a world or save one, depending only on which way it pushes and how long it has to work. A whisper, repeated forever, becomes a shout. But sunlight does not only steer asteroids gently across space. On some of them, it does something violent. It reaches down, grabs hold, and spins them faster and faster until a few of them tear themselves to pieces. The gentle warmth of sunlight has a wilder cousin. On some asteroids, sunlight does not just steer them, it spins them, faster and faster until they can rip themselves apart. We saw that an asteroid gives off heat as it rotates, and that escaping heat gives it a tiny push. Usually that push nudges the asteroid along its orbit, the Yarkovsky effect. But the very same escaping heat can also do something else, depending on the asteroid's exact shape. It can twist the rock, adding a tiny bit of spin, making it turn a little faster. Here is why shape matters. Most asteroids are not smooth balls. They are lumpy, jagged things covered in bumps, ridges, and odd angles. When heat radiates off an uneven, lopsided surface, the tiny pushes do not perfectly cancel out. They add up to a slight twisting force, always turning the asteroid the same way, speeding up its spin bit by bit. This twisting version of the effect has its own name, the Yorp effect, but you can just think of it as sunlight quietly winding up atop. The twist is impossibly gentle. Like everything else in this story, it would take thousands or millions of years to noticeably change an asteroid's spin. But sunlight is patient beyond all measure. Year after year, the light keeps twisting, keeps winding, and the asteroid spins faster and faster with each passing age. There is nothing in empty space to slow it back down. Now think about what happens to something loose that spins too fast. Spin a bucket of water fast enough and the water climbs the walls and flies out. Whirl a merry-go-round faster and faster, and it gets harder to hold on until you are flung off. The faster something spins, the more it tries to throw its own pieces outward, away from the centre. Many asteroids are not solid rock at all. They are loose piles of rubble, heaps of stones and dust held together only by their own weak gravity, like a floating mound of gravel. As sunlight spins such an asteroid faster and faster over millions of years, the outward throw grows stronger and stronger until finally it overcomes the feeble gravity holding the pile together. And then the asteroid starts to fly apart. This is real. Astronomers have actually spotted asteroids in the act of breaking up, flinging off streams of rock and dust, spun to the breaking point by sunlight over long ages. Some asteroids fling material off their spinning equators. Some split into pieces. A few even become pairs, a big rock and a smaller chunk that got thrown off and now orbits alongside it, born from the parent asteroid tearing itself apart. Sit with that for a moment. A force so weak it loses to a paperclip on Earth can, given millions of years and the right lumpy rock, spin an entire asteroid until it shatters. Sunlight, the gentlest touch in the solar system, becomes a slow-motion wrecking force powerful enough to tear mountains of stone to pieces, one patient twist at a time. The theme keeps deepening. Light pressure is nothing in a moment and everything across eons. It steers rocks, shatters rocks, and shapes the whole family of asteroids drifting through space. But it does not stop at boulders. It reaches down to the tiniest specks of dust, and there it plays a slow, deadly trick that drags them one by one into the fire of the sun. The smallest players in the solar system are grains of dust, some no bigger than a speck of flour drifting between the planets. And sunlight plays a strange, patient trick on them, one that slowly drags them to a fiery death in the sun. You might think sunlight would simply blow these tiny grains outward, away from the sun, the way it blows a comet's tail. And for the very tiniest grains, that is roughly what happens. But for slightly larger dust grains, something sneakier unfolds, and it pulls them inward instead of pushing them out. This backward-seeming trick is called the Poynting-Robertson effect. Here is the idea, and it takes a little imagining. A dust grain orbits the Sun, moving sideways as it circles, the way Earth moves sideways around the Sun. Now, because the grain is moving sideways, the sunlight does not hit it from straight ahead in the grain's own point of view. It comes in slightly angled, tilted a bit forward, the same way rain seems to slant toward you when you run through it, even if it falls straight down. Think about running through vertical rain. The rain falls straight down, but because you are running forward, it seems to come at your face, slanting toward you. A dust grain circling the Sun feels sunlight the same way. Because the grain is moving sideways, the sunlight seems to come slightly from the front, tilted against its motion. And light tilted against your motion acts like a brake. That slanted sunlight gives the dust grain a tiny push backward against the direction it is orbiting. Bit by bit, the grain loses a little of its orbital speed. And when an orbiting thing slows down, it cannot hold its orbit as high, so it spirals inward, drifting closer to the Sun. The effect is heartbreakingly slow, like all of these, but over thousands and millions of years, the little grain spirals steadily inward, circling closer and closer to the Sun until at last it falls into the Sun's blazing heat and is destroyed. Sunlight, by the subtle trick of seeming to slant, sweeps its own dust inward and burns it away. This has a huge consequence you can actually think about. The solar system should be full of ancient dust left over from its birth billions of years ago. But it is not as dusty as it should be, because the Poynting-Robertson effect has been slowly sweeping the dust into the Sun the whole time. The Sun acts like a vacuum cleaner, using light itself to pull in and destroy the fine dust drifting around it, clearing space grain by grain over the ages. So where does the dust we do see come from? It has to be constantly resupplied, mostly by comets shedding material and asteroids colliding and grinding each other down. There is a slow, endless cycle. Comets and asteroids make new dust, and sunlight drags the old dust into the Sun. A great tide of tiny grains flows perpetually toward the fire, driven by the gentle slant of light. We have now watched light pressure work on every scale, from a single cell held in a beam, to sails between planets, to asteroids shattering, to dust spiraling into the Sun. Each time, the same weak force given enough time shapes the cosmos, but the grandest stage is yet to come. Light pressure does something so mighty that without it, the stars themselves could not exist as we know them. Look up at any star, including our own Sun, and you are looking at a war that has raged for billions of years. It is a battle between two titanic forces, and light is one of the fighters. A star is an enormous ball of gas, unimaginably heavy. Our Sun is so massive you could fit more than 1 million Earths inside it, and all that mass creates a crushing pull of gravity, aimed inward, trying to squeeze the entire star down toward its centre. Gravity never rests. It is always pulling the star inward, trying to collapse it into a smaller and smaller ball. If gravity were the only force, every star would crush itself into oblivion almost instantly. The Sun would collapse under its own titanic weight, crumpling inward until it vanished into a tiny point. So something must be pushing back, fighting gravity, holding the star up against its own crushing pull. Something aimed outward, strong enough to balance the weight of 1 million Earths. Part of that something is light. Deep in the core of a star, nuclear reactions blaze, fusing atoms together and releasing staggering amounts of energy. That energy pours out as light, a torrent of photons born in the heart of the star, all trying to escape outward toward the surface. And as those countless photons push their way out, they press on the gas around them. They push outward, against gravity. This is light pressure again, the same force we have followed the whole way, now working on the grandest scale imaginable. Inside a star, the outward push of all that light helps hold up the crushing weight of the entire star. Trillions upon trillions of photons, each carrying its tiny punch, together shove outward hard enough to fight the inward pull of 1 million Earths worth of gravity. Light holds the star up, so a star is a balance, a standoff. Gravity pulls in, light and hot gas push out. When the two forces match, the star sits stable and steady, shining calmly for billions of years, the way our Sun has and will. The peaceful glow of the Sun overhead is the visible sign of a violent tug of war held in perfect balance deep in its core. Think about that the next time you feel sunlight on your face. That warmth comes from photons that fought their way out of the sun's core, and on their way out they helped hold the entire sun up against its own gravity. The same push you cannot even feel on your skin is, inside the sun, strong enough to support a star. Scale changes everything. The feeblest force on Earth becomes a pillar holding up the heavens. This balance is confirmed, understood physics, the foundation of how we know stars work. Gravity in, light and pressure out, meeting in a standoff that lets a star live. It is one of the deepest truths in all of astronomy, and light pressure sits right at the heart of it. But here is where it gets frightening. This balance has a breaking point. Light pressure can hold up a star, yes, but there is a limit to how much star it can hold. Make a star too big, too bright, and the outward push of its own light stops holding it together and starts tearing it apart. There is a line no star can safely cross, and it has a name. Light pressure holds a star up. But push that idea too far, and it flips into something terrifying. There is a size beyond which a star's own light begins to destroy it. That line is called the Eddington limit. Think about what makes a star shine. The bigger and more massive a star is, the hotter and brighter its core burns, and the more light it pours out. A truly giant star is monstrously bright, blazing with the light of many thousands of ordinary suns. That is a staggering amount of light, all pushing outward, all trying to escape. Now recall that light pushes on gas. In a modest star like our Sun, the outward push of light is strong, but gravity is stronger, so the star holds together comfortably. But as stars get bigger and brighter, the outward push of their light grows enormous, and at some point, if a star is bright enough, the outward shove of its own light becomes as strong as the inward pull of its gravity. That balance point is the Eddington limit, named after the astronomer who first worked it out. At the Eddington limit, something dramatic happens. The star's own light is now pushing outward just as hard as gravity is pulling inward on its outer layers. Push even a hair beyond that limit, make the star even brighter, and the light wins. The outward push of the star's own radiation overpowers gravity and starts blowing the star's outer layers off into space. The star begins tearing itself apart with its own light. Picture a fire hose so powerful that it knocks over the very firefighter holding it. The star's light is that hose. In a normal star, the light hose is strong, but the firefighter, gravity, holds firm. In a star at the Eddington limit, the hose becomes so powerful it blasts the firefighter backward, ripping the outer star away and flinging it into space. The star's own brilliance becomes the thing that destroys it. This is real and shapes the lives of the biggest stars in the universe. The most massive, brightest stars live right near this dangerous edge, constantly on the verge of blowing themselves apart. They shed huge amounts of their own material into space, driven off by the ferocious pressure of their own light. Some of the mightiest stars we know are visibly bleeding themselves away, hemorrhaging gas because their light is too strong for gravity to fully contain. Sit with the strangeness of that. For a small star, light is a helper, holding it up against gravity. For a giant star, that same light becomes a destroyer, blasting its outer layers into the void. The exact same force, the push of light on gas, saves one star and dooms another. The only difference is how much of it there is. The Eddington limit is a real boundary written into the laws of physics, confirmed by watching how the biggest stars actually behave. It marks the razor's edge where light pressure stops holding a star together and starts ripping it apart. And it does far more than just endanger giant stars. It sets a hard ceiling on how enormous any star is allowed to become in the first place. The Eddington limit does something profound to the whole universe of stars. It sets a maximum size. There is a ceiling on how big a star can be, and light pressure is what enforces it. Think about how a star grows. A star is born from a giant cloud of gas and dust, collapsing under gravity, pulling more and more material inward, piling on mass, growing heavier and brighter as it forms. You might imagine a star could just keep growing forever, gobbling up more and more gas until it becomes truly gigantic without limit. But it cannot. As a forming star piles on mass, it gets brighter and brighter, and the brighter it gets, the harder its own light pushes outward. At some point, the growing star reaches the Eddington limit, where its light shines so fiercely that the outward push equals the inward pull of gravity. Now, when more gas tries to fall in and join the star's own light blasts that gas away before it can land. The star slams its own door shut, so the star's brilliance becomes a shield against its own growth. Try to feed it more gas, and the light shoves the gas right back out into space. This puts a firm ceiling on how massive a single star can become. There is a heaviest possible star, and it exists because beyond that size, the star's light would simply refuse to let any more material join it. Light pressure caps the size of stars. This is why, when astronomers survey the heavens, they find plenty of small stars, fewer medium stars, and only a rare handful of true giants, with an upper limit that nothing seems to cross. The very biggest known stars cluster near a ceiling and go no higher. That ceiling is set by light pressure, the same feather-light force we started with, now dictating the largest objects that can burn in the sky. Think about the long journey this force has taken across our story. It began as a push too weak to feel on your hand, a curiosity that loses to a paperclip and gets beaten by a breath of warm air. And here it stands, at the largest scale of all, deciding the maximum size of stars, shaping the entire population of suns scattered across every galaxy. The weakest force on Earth writes the rules for the mightiest objects in the cosmos. There is a humbling beauty in that. The same physics that lets a beam hold a single living cell, the same push that drives a solar sail, the same warmth that spins asteroids apart, reaches all the way up to set limits on the stars themselves. One rule, running from the smallest speck to the greatest sun. Light carries a punch, and that punch shapes everything top to bottom. We have followed light pressure across the entire universe now, from a cell to a spacecraft to a star. But we have saved one of the boldest ideas for the home stretch. If light can push a sail and push a star's gas outward, then a wild question waits. Could we build an engine that runs on pure light, an engine that shoots out light itself as its exhaust and reaches the ultimate speed the universe allows? Every rocket works by throwing something backward. Burn fuel, shoot the hot gas out the back, and the rocket lurches forward. Throw exhaust one way, and you go the other way. That is how every rocket that has ever flown works, from a firework to a moon rocket. Now think about the fastest possible exhaust. The faster you throw your exhaust backward, the more push you get and the more efficient your rocket becomes. Ordinary rockets throw out hot gas moving fast, but nowhere near the ultimate limit. So what is the fastest thing anything can move? Light. Nothing in the universe moves faster than light, which raises a dizzying idea. What if you built a rocket that threw out pure light as its exhaust? This is the photon rocket. Instead of burning fuel and shooting out gas, it would produce an intense beam of light and fire that beam out the back. The light carries momentum, as we have learned all along, so shooting it backward would push the rocket forward. And since light moves at the fastest speed there is, this would be the most efficient exhaust physically possible. No exhaust could ever be faster. The beauty of the photon rocket is that it uses the exact principle we have followed the whole way. Light carries a punch. Fire that punch backward, and you get pushed forward. A photon rocket is the ultimate expression of everything in this story. A machine that turns the momentum of light directly into motion, with the fastest exhaust the universe permits. In principle, a photon rocket could reach speeds no ordinary rocket ever could, creeping closer and closer to the speed of light itself, the ultimate speed limit of the universe. Because its exhaust is already moving at the maximum speed, it squeezes the most possible push out of every scrap of energy. For crossing the vast emptiness between stars, this sounds like the dream engine, the one that could finally take us to other suns. There is a brutal catch, and honesty demands it. Light carries momentum, but not very much momentum for the amount of energy it takes to make it. To get a strong push from a photon rocket, you would need to produce a truly staggering, almost unimaginable amount of light energy, far beyond anything we can make today. The push you get for all that energy is tiny. So while a photon rocket is possible in theory, building a useful one is wildly beyond our reach right now and may stay that way for a very long time. This is the honest truth about many light pressure dreams. The physics is sound and confirmed. Light pushes, and in principle you could ride that push to incredible speeds. But light's punch is so gentle for the energy involved that turning the idea into a real powerful engine is fearsomely hard. The dream is real. The engineering is a mountain we have barely started to climb. Still, the photon rocket teaches something wonderful. Every rocket, in a sense, already pushes with a little light, and that hints at a funny truth hiding in your own home. You're probably holding a photon rocket right now, or you own one, and you never knew it. It is the weakest rocket ever made, and it proves the principle every time you switch it on. Here is a strange and delightful fact. You almost certainly own a rocket. It is sitting in a drawer somewhere, and you have used it 100 times without realizing. It is your flashlight. Think about what a flashlight does. You switch it on, and it shoots a beam of light out its front. That beam is a stream of photons, each one carrying a tiny bit of momentum, all flying forward, away from the flashlight. And by everything we have learned, shooting momentum out one direction pushes you the other direction. So when you turn on a flashlight, the flashlight is very gently pushed backward, in the opposite direction of its beam. Your flashlight is technically a photon rocket, a real one. It shoots light out the front and it gets a tiny push toward the back, exactly like the ultimate star engine we just imagined. The only difference is strength. Your flashlight's push is beyond feeble, so absurdly weak that you could never notice it in a million years. Just how weak? If you floated in empty space perfectly still and switched on a bright flashlight, it would push you backward. But the push would be so tiny that to build up even a slow walking speed, you would have to leave the flashlight on for many thousands of years without stopping, its batteries magically never dying. The push of a flashlight is real, and it is almost nothing, the gentlest rocket ever held in a human hand. Yet, it is real. That is the whole point. The exact same principle that could one day drive a starship works in the flashlight in your junk drawer. Shoot light one way, get pushed the other way. There is no difference in the physics, only in the scale. Your flashlight and a theoretical photon starship obey the identical law. One is just unimaginably more powerful than the other. This is a perfect little window into the whole story we've been telling. Light pressure is everywhere, in everything that glows. Every light bulb in your house is gently pushing back against its socket. Every candle flame nudges the air. The sun, shining on a planetary scale, pushes with a force that steers asteroids and holds up stars. And your humble flashlight, on the smallest human scale, is a genuine rocket, proving the principle with every click of its switch. There is something wonderful about that. The grandest ideas in physics, star engines, and interstellar sails are not separate from your daily life. They are the same physics you hold in your hand every time you need to find something under the couch. The universe does not have one set of rules for stars and another for flashlights. It has one set of rules, running from the drawer in your kitchen all the way to the edge of the galaxy, so light pushes always everywhere on everything it touches, on you, on comets, on sails, on atoms, on asteroids, on the guts of stars, and even, ever so faintly, backward on the flashlight in your hand. This endless universal push has one more surprising place it shows up, and it costs real money and real effort to deal with. Every spacecraft humans send into deep space slowly drifts off course, nudged by sunlight, and engineers have to fight that drift the whole way. When engineers send a spacecraft on a long journey across the solar system, they face a sneaky problem that comes straight out of everything we have learned. Sunlight keeps pushing the spacecraft off course gently but relentlessly, and if they ignore it, the ship misses its target entirely. We have seen that sunlight pushes on everything. A spacecraft is no exception. As a probe cruises through space toward a distant planet, sunlight strikes its body, its antennas, its solar panels, and gives it a constant, gentle shove. On any single day, the push is tiny, far too small to matter. But space journeys last for years, and the push never stops. Over a voyage of years, that endless little shove adds up. The spacecraft drifts slowly off its intended path, pushed sideways by the pressure of sunlight until it is aimed at empty space instead of its target. A probe headed for a distant planet could sail right past it, missing by a huge distance, all because of a force lighter than a whisper acting patiently over years. This is not a rare or minor worry. It is a real, everyday challenge that engineers must handle for essentially every deep space mission. When they plot a spacecraft's course, they have to include the push of sunlight in their calculations, treating that feather-light force as a real influence on where the ship will end up. Ignore it, and after years of flight, the probe arrives at the wrong place. To fight it, engineers do a few clever things. They carefully model exactly how sunlight will push on the spacecraft based on its shape and how its surfaces face the sun. Then they plan tiny course corrections along the way, small nudges from the ship's thrusters that cancel out the slow drift caused by sunlight, keeping the probe locked onto its target across hundreds of millions of miles. Some missions have to be especially careful because their spacecraft have large surfaces that catch a lot of sunlight, like big antennas or wide solar panels. The more surface facing the sun, the more push it catches, and the more the spacecraft drifts. Engineers sometimes even use the spacecraft's own panels like tiny sails, angling them to let sunlight help steer the ship, turning the enemy into a helper. Think about what this means. The same force we started with, the one too weak to feel on your hand, the one that loses to a paperclip, is powerful enough to knock a spacecraft off course over the span of a mission. Every probe humanity has sent to the outer planets has had to reckon with the push of sunlight. It is a real cost, a real complication, and a real triumph that we understand it well enough to correct for it precisely. It also proves, one more time, how this gentle force refuses to be ignored. On the ground, we brush it aside. But the moment we leave Earth and travel far enough, sunlight becomes a constant hand on the wheel, always pushing, always demanding attention. To cross the solar system, you must respect the push of light every single day of the trip. Sunlight shapes the paths of our spacecraft. It also shapes something far more beautiful and ancient: the great glowing rings that circle the giant planets, and the strange patterns of dust scattered throughout the solar system. The giant planets of our solar system wear rings, vast circles of ice and dust and rock spinning around them. The rings of Saturn are the most famous, a dazzling set of bright bands wide enough to stretch most of the way from Earth to the Moon, yet in places thinner than the height of a house. And light pressure helps sculpt them. Rings are made of countless particles, ranging from big chunks of ice down to grains of dust finer than powder. The big chunks are heavy enough that sunlight barely nudges them, but the tiny dust grains, feather-light and easily pushed, feel the pressure of sunlight strongly, just as comet dust does. And that push shapes where the fine dust in the rings can go. We have already met the tricks light plays on dust. Sunlight can push tiny grains outward, and through the Poynting-Robertson effect, it can drag orbiting grains slowly inward toward the planet or the sun. Inside a ring system, these forces are constantly at work on the smallest particles, herding them, moving them, deciding which grains stay and which get swept away. The delicate structure of the dusty parts of rings owes a debt to the push of light. Light pressure also helps explain some of the strange, faint patterns of dust scattered across the whole solar system. Beyond the bright rings, there are thin veils and bands of dust drifting through space, and their shapes are partly carved by sunlight pushing on the tiniest grains, sorting them by size, sweeping the smallest ones into particular paths. The fine dust of the solar system arranges itself, in part according to how hard sunlight can push each grain. Here is the key idea that ties it together. Sunlight sorts dust by size. A big grain barely feels the push and stays put. A tiny grain feels the push strongly and gets moved, swept, or flung. So over time, sunlight naturally separates the fine dust from the coarse, sending different sizes to different places, sculpting patterns out of what would otherwise be a shapeless cloud. Light becomes a sorting hand, arranging dust across millions of miles. There is real beauty in this. When you see a picture of Saturn's glowing rings, you're looking at a structure partly shaped by the same force that pushes on your hand in the sunlight. The gentle push of light, acting on trillions of tiny grains over vast stretches of time, helps carve those delicate bands and veils into the ordered, glowing shapes we find so breathtaking. It is the same lesson yet again, wearing new clothes. Light pressure is nothing to a boulder and everything to a dust grain. And because space is full of dust, light pressure is quietly at work everywhere, sorting and shaping and sculpting the finest material in the solar system into rings and bands and veils. The weakest force becomes an artist, and its canvas is the dust of 100 worlds. We have now traced the push of light across nearly every corner of the cosmos. Yet after all of this, after 2 centuries of study and proof, there is still an argument the experts have not fully settled. It sounds simple, almost childish, but it has puzzled brilliant minds for 100 years. How much does light push when it travels not through empty space but through something clear, like a piece of glass or a drop of water? After everything we have learned, you would think scientists have light pressure completely figured out. In empty space, they do. But there is one deceptively simple question that has sparked an argument lasting more than 100 years, and it is still not fully settled. The question is this: we know how much momentum light carries in empty space. But what happens to that momentum when light travels through a clear material, like glass or water? Does the push get stronger or weaker when light moves through something instead of through emptiness? It sounds like it should have an easy answer. It does not. Here is why it gets tricky. When light enters glass or water, it slows down. Light moves slower through glass than through empty space, then speeds back up when it comes out the other side. And since light's momentum is tied to its speed and energy, changing how it moves through a material raises a puzzle. Does slowing down mean the light now carries more punch, or less? 2 brilliant scientists came up with 2 different answers long ago, and both seem to make sense. One answer said light should carry more momentum inside a material, because the material concentrates it somehow. The other answer said light should carry less momentum inside a material because it slows down. Both were proposed by respected physicists, and both had solid reasoning and even some experiments backing them up. The 2 answers disagreed, and neither side could fully defeat the other. The debate became famous, a puzzle that would not die. For over a century this argument simmered. Experiments were done, and confusingly some seemed to support one answer while others supported the rival. It was as if nature was giving 2 different results depending on exactly how you asked the question. Careful, brilliant people looked at the same problem and came away disagreeing. This is confirmed to be a genuine, long-running scientific puzzle, not a settled fact. The likeliest resolution, which many scientists now lean toward, is subtle and a little mind-bending. It seems that both answers can be correct, because they are secretly measuring 2 slightly different things. Depending on exactly what you mean by the momentum of light inside a material, and how you account for the material itself getting pushed and squeezed, you can end up with either answer. The 2 rivals may have been describing 2 true halves of a single, more complicated picture. Even so, physicists still debate the finer points. The exact way light hands its momentum to a material, grain by grain and atom by atom, remains an area of active study and honest disagreement. After 200 years of triumphs, from Maxwell to solar sails to Starship Dreams, the humble question of how hard light pushes inside a piece of glass still has scientists scratching their heads. There is something wonderful about that. It reminds us that science is never truly finished. Even the parts we think we have mastered can hide deep puzzles, waiting patiently for someone to look closely enough. Light pressure has been studied for 2 centuries, and it can still surprise the smartest people alive. And that unfinished quality points us toward the biggest open question of all, the one that has haunted this entire journey. We have used light to sail between planets, but could light ever truly carry human beings across the vast gulf to another star? That dream is still unwritten. We come now to the greatest open question in this whole story. We have watched light push spacecraft, drive sails, and fling tiny chips toward the speed of light in our dreams. But could a beam of light ever truly carry human beings all the way to another star? Nobody knows yet. Everything we have learned says the physics allows it, at least in principle. Light carries momentum. A mirror doubles the push. A sail catches that push and speeds up without any fuel. Give it enough time or a powerful enough laser, and a sail can reach a real fraction of the speed of light. On paper, the road to the stars is open, paved with photons. But the leap from a tiny chip to a living human being is staggering. A person, plus the food, water, air and shelter to keep them alive for years, weighs a colossal amount compared to a postage stamp-sized chip. Pushing that much mass to the speeds needed for a star voyage would demand light energy on a scale that dwarfs anything humanity can currently produce. The gentle push of light, so perfect for a featherlight sail, struggles mightily against the heavy burden of a human crew. There are other monstrous hurdles too, and honesty requires facing them. A trip to even the nearest star would take many years, perhaps decades, even at a fraction of light speed. The crew would have to survive that whole time in the deadly cold and radiation of deep space. And a light sail, once launched, has no easy way to slow down and stop at the far end, since the pushing light is behind it, not ahead. Stopping at the destination is a problem nobody has fully solved, so the honest answer is that we do not know if a light can carry us to the stars. The principle is proven. Sails fly, light pushes. But scaling that up to a crewed starship crosses into territory where the challenges are so vast that no one can yet say whether they can ever be overcome. It might take centuries of progress. It might turn out to be possible only for tiny robotic probes, never for people. The question remains genuinely open. What we can say is that light pressure is the most promising known path we have. It needs no new laws of physics, only enormous engineering. Unlike wilder dreams that would require bending the rules of the universe, a light sail uses forces we understand completely and have proven again and again. If humans ever do sail to another star, there is a real chance that light will be the thing that pushes us there. Sit with the wonder of that possibility. The same faint force that presses on your hand in the sunlight, too weak to feel, might one day be the wind that carries our descendants across the black ocean between the stars to stand beneath a different sun. The gentlest push in nature could become the vehicle for humanity's greatest journey. Whether it will, no one alive can say. That uncertainty is not a disappointment. It is an invitation, a door left open for future minds to walk through. But there is one final thought this whole journey leaves us with, deeper than any spacecraft or star. Light pressure forces us to rethink the most basic idea of all, the simple, everyday meaning of the word push. We have travelled a long way together, from the sunlight on your hand to the dream of sailing to another star. And the strangest gift of this whole journey is not any spacecraft or star. It is what light pressure does to a simple word we thought we understood, the word push. Before this, if someone asked you what a push is, you would have a clear picture. A push means something solid or heavy pressing against something else. A hand on a door, wind on a sail, a wave against your legs. Every push you have ever known came from stuff with weight, stuff with mass shoving against other stuff. Push meant matter touching matter. Light shatters that simple picture. Light has no mass. It weighs nothing at all, and yet it pushes. It moves comets, drives spacecraft, spins asteroids apart, holds up stars, and presses ever so gently on your skin right now. A thing with zero weight reaches out and shoves the heaviest objects in the universe. The old meaning of push, matter shoving matter, simply cannot explain it. So light forces us to grow the idea. A push, we now understand, does not require weight. It requires momentum, that hidden punch a thing carries. And momentum does not have to come from mass. It can come from pure energy racing at the speed of light. This is the deep truth we uncovered, the one that took the greatest minds 2 centuries to prove. Energy in motion carries a punch, and that punch can move matter, with no mass behind it at all. That single idea rewired how we understand reality. It means the universe is full of pushes we never suspected. Every beam of light, every glow, every ray of sunshine is quietly shoving on everything it touches. The cosmos is not a place where only heavy things can push. It is a place where even weightless light presses on the world, shaping dust and stars and the paths of spacecraft. Push is everywhere, in every ray of light, all the time. Look back at how far this one truth carried us. It explained the comet tails that frightened our ancestors. It let a Russian scientist catch a force lighter than a shadow. It powered sails that flew between planets and dreams that reach for other stars. It gave us hands of light to hold living cells, deep freezers colder than space, shields against killer asteroids, and the very rule that holds up every star in the sky. All of it flowed from one strange fact. Light, weighing nothing, can push. And that is the thought to carry with you when you step outside. The next time sunlight lands on your face, remember, those photons traveled through space to reach you, and as they arrive, they are pushing on you, softly, endlessly, aiming you outward into the cosmos. You cannot feel it. It is as real as the ground beneath your feet. You are being pushed by light right now, along with every comet, every star, and every world in the sky. The universe pushes without hands, it shoves without weight. And once you truly understand that, you never look at a beam of light the same way again. The gentlest force we know turns out to be one of the most powerful architects of everything that exists. Light has no mass, and still, it moves the world.